Okay, the last major topic in section 14.7, finding absolute maxima and minima on closed bounded regions. Before we get to the Calc 3, the multivariable calculus part here, I think it's worth just remembering what does it mean to find absolute maxima mins, global maxima mins in the Calc 1 setting here. So let me draw some function. Okay, so suppose that this is our function f of x, and this is a, this is b. Let's say that we're trying to find global absolute maxima mins on the interval from a to b. So what do we have to do? We have to check critical points inside the interval a to b. So looks like there's a critical point right there. There's also a critical point outside the interval from a to b. We don't care about that. And we also have to check the endpoints of the interval. So check the function at a and check the function at b. So we evaluate the function at a at this critical point and at b, and we pick the largest and the smallest to be our absolute, our global max, and our global min. So looks like f of a is our global max, f of the critical point is our global min here. So something similar is going to happen when we're doing when we're trying to find global absolute max and mins of functions of two variables in closed bounded regions in 2D space. So suppose that I'm asking you to find absolute max and mins inside this square. So what would we do? We'd have to find all the critical points using the stuff that we did earlier in this section. Take the derivative, set it equal to 0, or see when the derivative doesn't exist, and you need both of the derivatives, partial derivatives, I should say, not just derivative, both the partial derivatives need to equal 0 for it to be critical points. So check the critical points inside, of course, and we have a critical point that's outside the region in question. We can safely ignore that. And then we also have to check the boundary. So I'm assuming this is a closed bounded region. Bounded means I can draw a circle around it without too much difficulty. Closed means that it includes its entire boundary, all 4 line segments there. And so when I say check the boundary, we're going to check, in this case, each one of these 4 segments here separately. And when we check each one of these 4 segments separately, this is going to turn into 4 separate baby little Calc 1 problems. So we're going to look for maxima mins on this line segment. We're going to look for maxima mins on this line segment, this line segment. And by doing that, we're going to look for critical points and endpoints of the line segment. So that is what we are going to be up to here. And then, of course, to kind of conclude everything, you're going to evaluate the function at all of your possibilities, and you're going to pick the absolute max, pick the biggest, and pick the smallest to be your absolute min. Okay, so without further ado, let's do an example of this. Find the absolute max and min values of f of xy is 2 plus 2x plus 4y minus x squared minus y squared on the triangular region in the first quadrant bounded by the lines. Let's draw this. X is equal to 0, y is equal to 0, y is equal to 9 minus x. Okay, so let's get to work. What's the first thing we should do is that we should find interior critical points. And we do that, of course, take the partial derivatives and set it equal to 0. So the partial derivative of f with respect to x is 0 plus 2 plus the derivative, the partial derivative with respect to x is 0 minus 2x. Partial derivative of this respect to y is 0 plus 4 minus 0 minus 2y. Okay, so we're never going to have the partial derivatives be undefined here. So when are these equal to 0? X is equal to 1, y is equal to 2. So our point here in question is going to be 1, 2. And sure enough, that falls somewhere in the interior of our triangle, so that's a good one. Okay, so next up we'll be checking the three boundary sides here. But before we do that, I want to start making a list of candidates. So by list, I just want to keep track of all the potential points. I think there will be 6 or 7 of them by the end, and then we'll check them all at the end. So first is that we have an interior critical point. So that was 1, 2, and so we'll list off about 5 or 6 more coming up. Okay, so now let's go ahead and check this side here. So this is the side when x is equal to 0. And this up here would be 0, 9. And this is, as I said, when x is equal to 0. So what happens? So let's go ahead and plop in. Let's go ahead and plop in, this is when x equals 0. We're going to plop in x equals 0 into our function, f of 0, y. This is going to become a function of one variable, just a function of y. So what happens here, we end up with 2 plus 2 times 0 is 0, plus 4y minus 0 squared minus 0 minus y squared. So this right here is just a function, of y on the interval y is running from 0 to 9. To emphasize the function just of y, let me just write g of y is equal to 2 plus 4y minus y squared. And now this is a Calc 1 problem. Find, global max/min of this function on this interval. To do that, we need to take the derivative, set it equal to 0. 4 minus 2y is equal to 0. That will be when y is equal to 2. We know that x is equal to 0. So our critical point here on the boundary is 2, 0. Also, we have to include the endpoints, 0, 0, and 0, 9. So at this point, let's update our list of candidates. So we have a boundary critical point at the point 0, 2. And then we have boundary endpoints at 0, 0, and 0, 9. Okay, so one side down, 2 sides to go. Let's do this side here. This is when y is equal to 0. So this is y is equal to 0. It runs from 0, 0 to 9, 0. So same as before, let's plug in. Y is equal to 0. So f of x, 0. 2 plus 2x, that's 0, minus x squared, and that's 0. So to emphasize as a function just of one variable, just of x, I'm going to write as h of x is 2 plus 2x minus x squared. We are optimizing on the interval from 0 to 9. So h prime of x is 2 minus 2x, that's equal to 0. We get a critical point, x is 1. Of course, y is 0. So the critical point here is going to be 1 comma 0. And of course, we have the two endpoints here of this interval, 0, 0, 9, 0. So let's add these to our list. So we have 1 comma 0 is another boundary critical point. 0, 0 is already on our list. 9, 0 is a new boundary endpoint. Okay, so we've got 6 here. I think there's going to be one more. So finally, we have to take care of the last side when not y is equal to 9 minus x. So that's going to run from, so this is 0, 9 down to 9, 0. So what we're going to do, y is equal to 9 minus x, we're going to replace y here with 9 minus x. F of x comma 9 minus x is equal to, so 2 plus 2x plus 4 times 9 minus x squared minus y squared becomes 9 minus x quantity squared. So this is once again for the last time. I should say the boundaries, the interval we're doing this on is x runs from 0 to 9. This is a function of one variable. This is just a function of x. Let me call this j of x is equal to this expression. When I'm just going to skip the details, when you algebraically manipulate this and simplify this, you end up with negative 43 plus 16x minus 2x squared. Okay, so we're trying to minimize this on the interval from 0 to 9. J prime of x ends up as 16 minus 4x. Set this equal to 0, and you get x is equal to 4. When x is equal to 4, y is 9 minus 4. Y is 5, so we have the point 4 comma 5. And again, we'd have the endpoints 0, 9 and 9, 0, but those are already on our list. So boundary critical point is 4 comma 5. So we found 6 potential candidates. Let's just plot them all. 1, 2 is in the middle. We have the 3 corners here. 0, 9, 0, 0, 9, 0. Boundary critical point at 0, comma 2. Boundary critical point at 1, comma 0. And a boundary critical point off here at 4, comma 5. So how do we find all of this stuff? We found this one, interior critical point from earlier in the section, and then the other 6 here, 3 endpoints of those line segments, and then critical points of the one variable functions on each of those line segments. Okay, so the very last thing that we have to do here, is to plug in these 7 points into this function here. So now I'm just going to say f of the point here. F of 0, 0, plug in zeros in there, we get 0. F of 1, comma 0, and we plug in x is 1 and y is 0. We get 2 plus 4. 2 plus 2 is 4, minus 1 is 3. Plugging in 0, 2, so that would be x is 0, so those go away. Y is 2. 2 plus 8 is 10. Minus 4 is 6. And so we can add that to our list. 0, 9. Plug in x is 0, y is 9. So those go away. 2 plus 36 is 38. Minus 81 is minus 43. That's pretty small. 9, 0. So let's plug in x is 9, y is 0. 2 plus 18 is 20 plus 0. Minus 81. 20 minus 81 is negative 61. Minus 0. So that's even smaller. So then the last two, f of 1, 2. 2 plus 2 times 1 is 2. So that would be 4 plus 8 is 12. Minus 1 is 11. Minus 4 is 7. And then the last one, I was going to skip the details there. Plug in 4 and 5, you get negative 11. So what do we conclude here? What's our biggest and what's our smallest? This one is the smallest. And the biggest one here is 7. So to end this problem, let's say, so we're asked for the absolute max and min value. So the absolute max is 7 attained at the point 1, 2, the critical point in the middle of the region. And the absolute min is negative 11 attained at the point 4, 5. So yeah, that takes care of, so this is where the absolute max was, that's where the absolute min were. But yeah, so this is I should say, this is a very long video, but it's a relatively straightforward process. It just is a lot of chugging away at things.